talk about the derivative as a rate of change. So we're going to let s of t be a function giving the position of an object at a particular time t. So this position, this is the dependent variable, and the time is the independent variable. Okay, so to make it perfectly clear, the position s depends on what the time is, and at different time t, we'll have different positions. So another idea besides position that we care about is we care about velocity. So the velocity of an object at time t, that is going to be given by the function v of t. And how is v of t calculated? V of t is really the derivative of the position function. So related to velocity is this idea of speed. And speed of an object at time t is given by the absolute value of the velocity function. So basically, for us, velocity actually has a sign associated with it. It could be positive or it could be negative. Positive usually means the object's going forward. A negative velocity would mean the object is going backward. When we look at the speed of the object, we don't care whether it's going positive or negative. We just know what the magnitude of the velocity is. So the speed has no direction. No direction, or you could think of this as it has no sign. Okay, so it's always positive. For example, if I'm driving forward, my velocity could be 55 miles per hour. If I was driving backwards, my velocity would be negative 55 miles per hour. But when I calculate the speed is just 55 miles per hour. All right. Another thing that we care about, we definitely care about something called acceleration. And acceleration is the rate of change of the velocity. Okay, so velocity is how fast your position is changing, and acceleration is how fast your velocity is changing. So acceleration is described as a of t, and that's really equal to the derivative of the velocity, which is equal to the second derivative of the position. Okay. Why don't we take a look at an example together? Let's take a look at example 1. A ball is dropped from a height of 64 feet. So the fact that this is dropped is important. I'm going to highlight that. And its height above ground in feet t seconds later is given by this equation right here. So this is our position function. And the question asks, what is the instantaneous velocity of the ball when it hits the ground? So we need to figure a couple things out. The first thing that we need to figure out is we need to figure out, when does the ball hit the ground? When does the ball hit the ground. And you have to ask yourself, does when the ball hit the ground, is that a position thing? Is that a velocity thing? Or is that an acceleration thing? And this is actually a position thing. So the ball hits the ground when the position s of t is equal to 0, because 0 is considered ground level. So what we need to do is we need to take our position function. We'll set 0 is equal to negative 16t squared plus 64. Okay, and we want to solve that. So when we solve that, what do we get? Well, we're going to move the 16t squared to the left-hand side. So we're going to get 16t squared is equal to 64. Then we can divide both sides by 16, and we're going to get t squared is equal to 4. And what this means is that t is equal to plus or minus 2. Now, we're not allowing time to be negative, so really this tells us that our t is equal to 2 seconds. Okay. Now that we know the time when we hit the ground, the next thing we want to know is what's the velocity when we hit the ground. So what's the velocity when the ball hits the ground? I mean, this is really what the question was originally asking, but we couldn't answer that until we had this time at our fingertips. So because this situation involves velocity, we want to use the velocity function. And the velocity function is really the derivative of the position function. So we need to basically differentiate with respect to t, our position function, which was negative 16t squared plus 64. Remember, I put my differentiation operator as d over dt because the independent variable is t. Okay? All right, so let's take the derivative. When we take the derivative, we're going to get negative 32t plus 0. Now, to answer this question, all I need to do is take the time I found earlier and plug that into the velocity equation. So v of 2 is going to be equal to negative 32 times 2. And when I simplify that, I'm going to get negative 64. And now I need to worry about the units. So the units for the position were feet, so the numerator should be feet. And my independent variable was time, so time was measured in the units of seconds, so this will be feet per second. And this is our answer to this question. All right. Let's scroll down a little bit. We can answer part B together in class later. I really want to finish off this video by answering this question right here. How do I determine whether an object is speeding up or slowing down? So we're worried about speeding up versus slowing down. Okay. So the first thing I want to mention to you is that this depends on two things. It depends on velocity, and it also depends on acceleration. So speeding up means the velocity is getting faster and faster, whereas slowing down means the velocity is getting slower and slower. Okay, so the way that we can determine if the object is speeding up or slowing down is we're going to look at the signs of each of these functions. So I should really say this depends on the signs of the velocity and the acceleration. Now, if the velocity, I don't want to keep writing the words, so I'm going to put v of t. If v of t and a of t have the same sign, the object is speeding up. If the velocity and acceleration have different signs, the object is slowing down. Let's break down a few different cases. So let's say that v of t is positive and a of t is positive at some time t. Then this means that the object is speeding up and going forward, because it's going forward because the velocity is positive. Okay? If our object, let's say the velocity was negative and the acceleration was also negative, then in this case, the signs are still the same, but they're both negative. So this is speeding up, but going backwards. All right. So if we have, if we have a situation where the velocity is negative, but the acceleration is positive, this means that it's slowing down, but it's going backwards. If the velocity is positive, but the acceleration is negative, this means it's slowing down forwards. All right, we'll work through some examples and talk about more about this in class. Take care, everyone.